All right, so in this video, we're going to be looking at the LU decomposition, which I think is a very fun and elementary way of introducing matrix factorizations or matrix decompositions. And I personally wasn't taught this in my intralinear algebra course. I'm not sure why, and don't let that sway you off because it isn't difficult. All the knowledge you have from Gaussian elimination is all you need for this. But I think it is a really fundamental matrix decomposition because it's certainly focused on a lot more in advanced linear algebra courses such as numerical linear algebra and like matrix analysis if you were to go on to take those. And I want to sort of stress again, I think I did this in part one, that these videos might not, probably won't match up with what you're doing in your linear algebra course. And I'm outlining them sort of as a course, but I'm using really a hodgepodge of like three different textbooks and my experience with my interlinear algebra course, but then also things that I think were important from maybe other linear algebra courses or just things I learned on my own that are especially necessary for applied math students. As someone who studied computational math and scientific computing, I think these topics are super important. And so that's probably why you'll see me focus mainly on solutions to ax equals b and really a lot more stuff involving matrices because they sort of split linear algebra up into maybe a pure math and an applied math section. In pure math, isn't necessarily interested in methods to finding ax equals b, but really the theory behind matrices and vectors and this more general idea of linear operators and transformations and stuff like that. And we will get around to all that. So if you're needing information on that, it will be here on the channel eventually. But today we're going to be looking at our first matrix decomposition. So a matrix decomposition is simply a way of taking some original matrix, say A, and expressing it as the product of what we generally call simpler matrices. Simple meaning that generally speaking, they're easier to do things with. They have nice properties. And so if we can find a decomposition involving these simpler matrices, then it makes our life a lot easier when trying to solve ax equals b. And so in this case, we're looking at two matrices L and U. And L is what's considered a lower triangular matrix with ones on the diagonal. And U is what's considered an upper triangular matrix. And U is what we gain from performing Gaussian elimination. And, I'll go now and talk a little bit about what lower and upper triangular matrices really are. Let's now look at a semi-formal definition of the LU decomposition. So let's take A to be just a square matrix in this case. And we're looking for factorization L times U, where L is lower triangular with ones on the diagonal, and U is upper triangular. Now, the way we achieve this is through Gaussian elimination without row swaps. Now, this part is pretty important. Um, Generally, for LU decomposition, there's what's considered LU decomposition without pivoting, LU decomposition with pivots, and LU decomposition with partial pivoting. Now, this terminology yields a whole bunch of different things as far as the LU decomposition is concerned. And that's why it's talked about in sort of later, more advanced courses, because you can really generalize this and make it a little bit more abstract than it is. What we're considering is square matrices only, and we're considering without row swaps, which means that we can find an explicit decomposition L times U, and we don't have to use something called a permutation matrix to find a decomposition that would be written as PA equals OU. So we're looking at just a super simple case for this, but if we can perform Gaussian elimination on our matrix without swapping rows, then we say that A yields a valid LU decomposition. And I want to express this because I know that when we talked about Gaussian elimination and elementary row operations, swapping rows is a valid elementary row operation. However, in this case of the LU decomposition, it's just not allowed for what we're trying to achieve. Let's now take a second to look at the structure of these matrices so we know what we're dealing with. So we're interested in these two matrices, L and U. Now, L is what's considered to be lower triangular. So as we can see from this matrix, we have ones all along the diagonal, some elements that we're calling little l below the diagonal, and then zeros everywhere else above the diagonal. This is what's called a lower triangular matrix. I'm sure you can see where the name comes from. It sort of forms this right triangle if you just look at everything from the diagonal down. And it's lower because we're only considering elements below the diagonal. Similarly, for an upper triangular matrix, I'm sure you could guess, we're considering the same structure. However, now we're considering elements only above the diagonal and zeros everywhere else below the diagonal. So when we find these two matrices, we find that when we multiply them together, if they're valid, we get our original matrix A as such. So now that we've sort of got the definition under our belt, let's actually look at finding a valid LU decomposition. So here's the process, generally speaking. We're going to consider some square matrix A, and we're going to perform Gaussian elimination on that matrix until we arrive at some echelon form, which we'll then use to form U, or that reduced form will be U. And while we're performing this Gaussian elimination, we're going to keep track of all the multipliers in order to form L. Now I'll talk about what multipliers are in a second. And while we're doing this, we want to, of course, remember that we're not allowed to swap rows at all in this case. So when we talk about multipliers, let's first consider, how we're writing row operations. Now, this is the general way we express a row operation. And if let's say we're looking at row 3 and row 2. So we're going to look at row 3 and perform an operation on row 3. So we'll say row 3 arrow, row 3 plus row 2. Let's just add row 2. So how do we fit that simple expression into this general definition where we have this minus of some multiple? Well, what is the multiple of row 2 in this case, plus row 2? Will just be positive 1. 1 times row 2 is just row 2. Okay, that's fine. So we're always considering this minus though. So how do we get a positive from this minus in our expression? Well, we just assume it to be negative because then we just have minus minus, which becomes positive. So we have minus minus 1, which is positive 1. So our multiplier would be negative 1. So now let's actually look at this system, super simple system, just 2 by 2, entries 4, 3, 6, 3. Now we only need to perform the following operation to reduce this. And so this will turn that 6 to a 0 and that 3 to a negative 3 over 2 or negative 1.5. So this is our operation, row 2 minus 3 halves row 1. So we know the multiplier of row 1 is 3 over 2, but what does its sign? Well, we see that it's minus here, so that means that our multiplier must be positive. And so as I've highlighted here, our L21 entry will be positive 3 over 2. So let's focus on this now. At this point, we have U. We've got it to an echelon form. This is our upper triangular matrix U. To find L, what we generally do is just initially consider the identity matrix with its valid dimension. So this will just be a simple 2 by 2 identity matrix because we want ones along the diagonal. And then we, of course, just fill in that 0 below the diagonal with what our multiplier is, which in this case is positive 3 halves. So now we have 1, 0, 1.51, which is our lower triangular matrix L. And thus we found a valid LU decomposition for this matrix. And I'll let you guys, verify the multiplication by yourself, but this is a valid decomposition. If you multiply these two matrices together, you will get back our original matrix 4, 3, 6, 3. So let's not look at a 3 by 3 system where we use the same rules as last time, but this time let's keep track of our multipliers. So our first operation, we're considering minus 2R1, so our multiplier is going to be positive 2. Then we're considering plus row 1, so our multiplier is going to be negative 1. And similarly, we're considering plus row 2, which is going to be negative 1 again. Now, at this point, we've found U, and let's go about constructing L in the same way where we first consider the identity matrix. And now let's just take our multipliers and plug them in respectively, being 2, -1, and -1. And now we found a valid LU. All right, now that we've found two valid LU decompositions, let's use this knowledge to actually solve the system AX equals B using the 3 by 3 decomposition that we just found. So we want to consider AX equals B, but now A is LU. So let's consider LUX equals B. Now, this isn't too helpful on its own because if we were to just solve this outright like we've been doing, we'd still have to multiply those two matrices back together and then we just end up with A. So we're not really achieving any efficiency. But fortunately, the LU decomposition gives us two very fundamental formulas that we can use in order to solve the system. So here's the process. Let's let's consider some new vector y and let it be equal to ux. Now that we have this, we're going to solve the following equation, Ly equals b, in order to find a vector y. This is what's called forward substitution. And then we'll use that vector y to solve ux equals y. And once we solve ux equals y for the vector x, that vector x is our solution vector to our system ax equals b, or lux equals b in this case. So let's look at how this goes. So we know what L is. We found that already. It's the following matrix. And we'll consider some solution vector B. Of course, this will be given to you. And we'll say it's 5, -2, and 9. So now we want to use this matrix L to solve this system for Y. So this is super simple because now that we're in lower triangular form, we have, first of all, a direct solution for y1, and then we could just do some simple plug and play to get the rest of our values. So we know y1 is going to be the value 5 as such. And now we'll use this to find y2, which will be -12. And now we'll use y2 to solve for y3, which will be 2. Great. Now we know that the vector y is 5, -12, 2. So now we can solve ux equals y, where u is our upper triangular matrix, x is going to be our solution vector, and y is the vector we just found via forward substitution. Now, this is called backward substitution, but we can follow a very similar process, but we're going to go backwards. Now we're going to consider x3 first, which we know will be the value 2, as shown. And then we'll use that to solve for x2, which will be 1. And then we'll use x2 to solve for x1, which will be 1. So we end up with the vector 1, 1, 2. And so what we've done is we found some vector y, use that to find our solution vector x, which then solves LUX equals b. And as we can see, our final answer is the solution vector 1, 1, 2. And that's all I have for this video. That's the LU decomposition in a nutshell, if you will. So next video, I'm going to start talking about vector spaces. So we're going to talk about what is a collection of vectors versus a vector space, what is a subspace, how to show that something is a subspace, how to show that something is a vector space. And it might seem trivial while we're doing the video, but this knowledge is very, very fundamental in linear algebra. So as always, if this was helpful to any of you, I hope you enjoyed. Thank you.